So thank you. I'll be talking about this phenomena called Converse Symmetry Breaking, and it's the work is in collaboration with Adilson, Motter, and our former postdoc Ferenc, Molnar. So what is this Converse Symmetry Breaking? Okay. So let me tell you in an example. Here's a network, an example of a network. A ring of 7 nodes with link strength in one direction is 1 plus delta, ring coupling strength in the other direction is 1 minus delta. So this has a rotational symmetry. And it's a coupled system, phase amplitude oscillator sitting on each node, each of them obeying this system of equation. So the angle variable theta is coupled through this term all to all in a global fashion, but the amplitude variable R is coupled through the network structure that you just saw through this adjacency matrix Aij. And here I'm going to focus on this parameter beta sub I, which controls the heterogeneity of oscillators, the symmetry of the system, because the network structure itself is symmetric. And now I'm going to focus on synchronous state of the system where the angle variables are running at the same speed omega and the amplitude are all equal to 1. So this state has the same symmetry as well. So if you choose beta sub I parameter value to be homogeneous across all the oscillators, and you start your system very, very close to the synchronous state, here's what happens. It starts to desynchronize because the state is unstable, despite the fact that I have actually chosen this 1.868 to be the best common value of this parameter in terms of the stability. But if you switch these values, adjust those values to a suitable combination across, now it's heterogeneous combination across the oscillator, you see that they quickly synchronize again. So this is the kind of phenomena that I'm talking about. In this particular example, a complete synchronization state that is stable, despite the fact that oscillators are made non-identical through these heterogeneous beta sub I values. But more importantly, because I chose the best homogeneous value of beta I and it was still unstable, the complete synchronization is actually stable only when you make the system asymmetric with non-identical oscillators. So the symmetric state is stable only if system has a broken symmetry. And this is something that you can consider as a converse symmetry breaking, because in the usual situation of symmetry breaking, what happens is that you have a symmetric system, the symmetric state of the system becomes unstable, so the only stable state is asymmetric. Here, what you saw is that stable symmetric state requires system to be asymmetric. So you see how the roles of the state and the system is switched, reversed, and that's why we call this converse symmetry breaking. So I'm going to show you that, show you a validation of this phenomena in a lab experiment, and also some demonstration in real world power grids. The experiment first. So this consists of 3 permanent magnet generators. They're chosen to be identical as within the experimental constraints. And to control the tunable parameter, in this case is damping coefficient, we put mechanical brakes on those generator shafts to adjust friction. And those generators are driven by DC motors and connected through an AC electric circuit in a symmetric way. So this allows us to model the system as a set of 3 coupled oscillators coupled in symmetrical way. And the equation of motion looks like this, where delta sub I is the angle, electrical angle of each generator. And beta I is the damping parameter that's tunable. In this experiment, we chose the generators to be identical. So except for this friction, the damping coefficient. So the other parameters are all going to be homogeneous, identical. So that makes the system rotationally symmetric. And we focus on a synchronous state again, but in this case, a splice state, because that's the convenient choice for this particular example in experimental setting, which is also rotationally symmetric. So it has the symmetry of the system. And we measure the stability using the maximum Lyapunov exponent, which is the largest real part of the eigenvalues of the Jacobian matrix of the system. And even if you consider noise in the system, you can show for two broad classes of noise dynamics that there is a threshold for this lambda max above which the synchronous state is unstable probabilistically, and below which the state is stable. So the simulation predicts, well, so using this lambda max, you can visualize the region of stability from numerical simulations. And on the right side, I'm showing a slice where inside the white curve is the stable region here and also here. And in the experiment, we chose this point where the beta 1, beta 2, beta 3 are homogeneous within experimental constraint. And this point inside the stable region that is predicted to be stable with homogeneous, heterogeneous values of beta sub I. So we went ahead and run the experiment with multiple runs, totaling in about an hour and a half of experiments, took measurements of time series of voltages, and identified the segments in the time series where the splice states are observed, hundreds of them. And what we did was for each segment, we estimated lambda max, and in particular, the improvement in lambda max, the stability, when you go from a homogeneous configuration of betas to the heterogeneous configuration of betas. And what we found was in almost all cases, the improvement is positive, which means that we have CSB confirmed in this experiment. Now to power grids. Turns out that the equation of motion is basically the same. It looks exactly the same. The only difference is that now, in order for the system to represent real system, you have to have the parameters determined based on real system data, like those particular systems that we looked at. Just to introduce notation here, the linearization of this model leads to a Jacobian matrix of this form, where matrix P is the effective coupling between the generators, which depends on the state, as I mentioned earlier. And B is the diagonal matrix with beta sub I on the diagonal. So this is where the tunable parameter is. And then we look at the same lambda max as a function of beta. And our previous work has shown that if under the constraint that beta sub I are homogeneous, the optimal stability is actually obtained in this special point where alpha 2 is the smallest non-zero eigenvalue of the coupling matrix P. Here, we found that allowing for heterogeneity in lambda beta sub I can further enhance the stability. And in fact, we see this in a wide range of conditions in terms of stress level in power grid, measured in terms of how much power is flowing from generators to consumers across 4 different examples that I'm showing here. So the improvement from the red curve to the blue curve is significant across a range. You can also plot the optimized parameters beta sub I on a map, and what it shows is that the heterogeneity of the optimized choice is actually in a non-trivial way distributed across geographic space. At least those 2 that for which I have the geographic information. Now, the challenge in establishing evidence for CSB, converse symmetry breaking in this context, is that the matrix P that comes from the structure of the network, the parameters of the real power grid, has heterogeneity on its own, and it's difficult to isolate the CSB effect from that. So we developed a method to do that in the case of pairwise permutation symmetry. So the idea is to find a pair of generators, like 6 and 7 here, for which the pattern of input strength are very similar to each other. So the left side and the right side looks very similar in terms of coupling. These are basically coupling strength. And construct a symmetrized version of the coupling matrix P prime, basically by imposing that the left side of the picture is exactly the same as the right side. When you do that, you can do the similar calculation, plotting lambda max as a function of the 2 beta values, beta sub I values for those two generators. And you indeed see that the optimal choice is off the diagonal, which means that it is achieved for different value of beta sub I for those 2 generators. And this is true for all those 4 examples here. And if you trace back from the symmetrized version of the coupling back to the original one by interpolating between them, you can see that the gain that you have in stability is actually maintained, at least to a large extent. So this serves as the evidence of CSV in those power grid systems. So I hope I convinced you that this effect is real in the sense that it has been confirmed in the lab experiment, as well as having evidence in real systems, in this particular case, power grids. And I want to end by mentioning that in our group, we have looked at various other aspects of this phenomena, including how prevalent this phenomena is across both experimental and theoretical models. And so there's a lot to look into here.